The human nervous system is an electrical network operating on measurable frequencies. Every cognitive state, from deep sleep to high arousal focus, is the direct physiological output of rhythmic electrical pulses firing across billions of neurons. Because this system is electrical, it is susceptible to a physical process called entrainment. This is the brain's inherent capacity to synchronize its internal neuronal firing rates with the rhythm of external stimuli, such as sound or light. Applying specific sound waves acts as a biological tuning fork. The nervous system aligns to the external rhythm, which physically modulates the brain's internal neurochemistry. To master this mechanism, we have to look at the exact wave mechanics of binaural beats, broadband noise, and cardiac coherence, mapping how each intervention alters human biology. These sound frequencies function as mechanical levers, used to force specific shifts in cognitive states by overriding the brain's default electrical patterns. Binaural beats are a neurological artifact rather than a naturally occurring ambient sound. They are generated entirely by the brain when it is forced to process two distinct signals simultaneously. If you play a 360 Hz tone into the left ear and a 400 Hz tone into the right ear, the brain cannot reconcile them as a single sound. It must process the mathematical difference between the two frequencies. These signals travel through the auditory pathways to the brainstem, converging in the superior Olivary complex, where the two distinct rhythms collide. To bridge the gap, the brain constructs a perceived third wave, pulsing at exactly 40 Hz, the precise offset between the two original tones. Once this 40 Hz rhythm is perceived, neurons in the auditory cortex physically alter their firing rates to match the tempo of this internal illusion. This provides a backdoor into the nervous system, allowing us to force the brain's architecture into a targeted oscillatory rhythm through simple frequency offsets. Brainwave states are categorized strictly by their frequency speed. On this spectrum, delta and theta represent the slow, low-frequency range, while alpha and beta represent the rapid, high-frequency range. Clinical data identifies the delta and theta ranges as effective tools for down-regulating the nervous system, and training the brain to these slow speeds helps mitigate both acute and persistent anxiety. Conversely, analytical focus requires the rapid firing of the beta state, specifically at 40 Hz. This 40 Hz entrainment directly stimulates the release of dopamine and acetylcholine. These chemicals physically drive the brain into a state of high arousal beta dominance. Precise targeting is critical. Studies show that applying slow theta frequency beats during complex tasks actively interferes with memory and analytical concentration. The specific Hertz target dictates the resulting neurotransmitter cascade, meaning these interventions must be tailored to the desired cognitive outcome. Focus does not operate as an instantaneous binary switch. Expecting the brain to snap immediately from a distracted state into deep concentration is a physiological impossibility. Concentration requires a progressive accumulation of epinephrine, acetylcholine, and dopamine. This chemical ramp-up follows a dynamic curve that typically takes several minutes to peak. Broadband acoustics, specifically white, pink, and brown noise, can expedite this transition. Unlike binaural beats, these consist of a continuous spectrum of ambient frequencies. These sounds amplify neuronal activity in the prefrontal cortex, the area of the brain responsible for directing and maintaining focus. By electrically stimulating the prefrontal cortex, broadband noise reduces the transition time required to enter a state of deep concentration. To optimize this, use 40 Hz beats or pink noise for a 5-minute warm-up phase. This primes the chemical environment before starting high cognitive load work. Internal entrainment is driven by the heart, the body's primary biological pacemaker. Its rhythmic pulses influence the electrical state of every other organ system. Heart rate variability, or HRV, measures the changing intervals between heartbeats. These intervals are a direct reflection of the balance between the sympathetic and parasympathetic nervous systems. When you consciously direct the heart into a rhythmic, sinus-like state called coherence, it creates systemic phase locking. This rhythm travels up the vagus nerve, pulling the brainwaves and other organ systems into a synchronized pulse. This timeline tracks a police officer during a high-stress training scenario. Following a tachycardic spike to 180 beats per minute, the heart rate remains at an elevated sympathetic plateau long after the event. At 11:54, the officer applies coherence techniques. This forces an immediate parasympathetic override, dropping the heart rate back to its baseline through intentional internal entrainment. This systemic synchronization creates an optimal physiological environment for recovery. By pulling the body's various organ systems into a single coherent rhythm, inflammation is suppressed and pain perception is modulated. This structural shift explains why coherence protocols have successfully reduced post-operative opioid use by 50% and accelerated skin cell regeneration in psoriasis patients by 400%. Cardiac phase locking is a physical intervention that halts the systemic sympathetic cascades that otherwise hinder healing and cognitive function. The human body is an integrated frequency environment. We are not tethered to our default chemical or emotional states. We can actively reshape them through external and internal levers. The toolkit is precise. We use binaural beats to trigger the acetylcholine required for focus, and broadband noise to prime the prefrontal cortex for work. We can employ cardiac rhythms to phase lock the autonomic nervous system, ensuring the brain and heart vibrate in a single coherent state. Repeating these oscillatory states triggers neuroplasticity. Over time, these patterns are etched into the nervous system, easing the return to focus and resilience. Routinely exposing the nervous system to precise auditory and cardiac rhythms structurally upgrades our baseline physiology, providing a permanent improvement in autonomic control and cognitive depth.